All right, we're here with Adrian Marinescu again, a kernel developer, and your specialty is the heap and other lower level issues.
Some other stuff.
So what are you working on these days? We've had you before.
Most of the time these days I'm working on the Heap Manager, I used to be more involved in other components such as the local specific or LPC and OJ management as well. But for Vista, a lot of the of my cycles were in the Heap Manager. Yeah. There are quite significant changes in the Heap Manager for performance, for security.
Excellent.
And the customers are going to see those.
So last time we had you on Channel 9, you talked about the Object Manager, as you mentioned you used to work on it. So now it's Heap Manager.
Yeah.
Can you briefly describe what the Heap Manager is, what the Heap subsystem is all about?
Sure.
As brief as you can.
Right. So, okay, so the Heap Manager basically allocates memory for user mode applications to store objects, structures, data. And it's a generic, infrastructure that the operating system offers for applications. And I can lay down a little bit like what is the position and the heap and how the heap management goes. Can I actually? Sure. Okay. Okay. So if you look from the programming perspective, here you have let's actually look at that line here. Here you have user mode, and here you have the kernel mode.
Yep.
And here you have application space, right? These are
the things that we use.
Yeah.
Right. Gotcha.
Right. I don't know, Internet Explorer and services, whatever. And most applications actually talk to allow the Win32 subsystem, where you have some functions such as heap alloc. I have a pretty ugly writing, so
that's okay. Heap alloc,
heap alloc, heap free, and a lot of other functions that start with the heap prefix.
Okay.
These are very thin layers on top on the heap management. In user mode, we have the most of the heap implementation in NTDLL. And we have RTL functions start with RTL, such as RTL allocate heap, RTL free heap, and so on, RTL create heap. Basically, the user mode heap management actually does some memory manager for small blocks, for larger blocks that come from kernel mode with virtual alloc and functions like that.
Okay.
There is also some option to have a heap in a section, in a map section as well, and it can be shared between kernel and user mode. That's kind of a very rare usage. Okay. Also for the applications perspective, you have the C runtime libraries, which is malloc free, where some implementation actually goes directly to the NT-Heap Manager. There are also a thin wrapper on top on the heap management. Some of them they have a very specialized heap implementation, such as the small block heap that's on in MSBCRT.
Okay.
So basically, this is kind of the area that I'm going to focus on, this part in the NTDLL. Okay. And as I said, the functions that come on top on this are very thin wrappers on top on the.
Okay, so what you're saying is that the Heap Manager runs in user mode.
Right.
In NTDLL.
Right.
And
most of the structure, most of the infrastructure.
Most of the infrastructure.
Yeah.
Okay. So let's talk about real quickly for people who don't know. I mean, what is the heap? Why is it called a heap? Do you just throw objects on it in some sort of
kind of
versus a stack, right?
Yeah.
Okay.
Okay, so the Heap Manager, you should just answer the very quick, simple question, such as someone wants to allocate, let's say, a buffer of 20 bytes, and you have to the Heap Manager is supposed to find the 20 bytes contiguous space somewhere in the memory, in the address space, and return to the user.
Great.
And there are a lot of versions and algorithms to implement heap management. And for every single one, you can find like some, some pluses, some positive sides, some have some negative side, and it really depends a lot of the application patterns. We also have to consider that lately the usage pattern actually changed. So if you look back, like 10, 15 years, the application used to allocate much less memory than we have today. So we had computer like few hundred megabytes now. Few megabytes that were shared.
Yeah.
And now we have gigabytes computer, and now we have high-end servers which have much more than this. And if we look at the 64-bit platform, we also see like even higher increase in the memory usage. Because also the limitation of the address space of being 2 gig or 3 gig sometimes is not longer a problem for 62-bit. So the heap management actually needs to adapt to those changes in the in the usage and for the application, so that will perform faster and will scale much better on multiprocessors.
Okay.
And as you know, lately the industry tends to have multiple chips on the same multiprocessor on the machine.
Sure.
And on the other side, the Heap Manager also works on a very with some changes. Anyway, some on C devices and small devices. So basically, you have to see here like the broader scale where this Heap Manager needs to to fit in.
Absolutely.
So from small devices to high-end servers.
Which is the case for the kernel in general, right?
Yeah.
It's a general purpose kernel.
Right.
Fantastic.
So
So let's talk about specifically the great work that you've done in Vista with relation to the Heap Manager. In other words, you've mentioned it's more secure. Can we talk about the security angle of the Heap for a little while?
Sure.
Because I know that that's been a popular
that's
security circles anyway.
Right, that's very popular subject. So actually, I'll need to provide a little bit some background about the security.
Sure.
So like a few years back, I don't remember exactly the years. I think like somewhere like 2002, 2001, that kind of time frame. There were like some well known to exploit heap vulnerabilities, which is like, let's say if you have an application running in Windows and has a buffer overrun. There were ways for hackers to take advantage of that buffer overrun and execute random or arbitrary code on the machine. Back then, it was a very there was some version of a very reliable method, which is so the Heap Manager keeps the blocks in a contiguous area, and each block has a header of 8 bytes. I'm just talking about the 32-bit platform here, right?
Okay.
I had a 8 bytes header here, and here is the the actual user data that the user holds on, and then is the next allocation also has like 8 byte header and so on. And on free blocks, the Heap Manager saves in the first 2 pointers the forward link and the backward link that the Heap Manager uses to manage the free blocks. So when someone frees an allocation, the Heap Manager uses these two and insert in one, actually multiple lists in the Heap Manager depending on the size. And later on, if someone requests from a similar size, may look up on that list and find the block.
Okay.
And the exploits back then were using like these two these pointers to write an arbitrary value at an arbitrary address. So if the program, let's say, had like 16 bytes buffer overrun, so that it overwrites over the header and this 4 pointer, right after returning this pointer, it may cause, let's say, this function, this buffer to be released. Or be allocated, and cause this arbitrary write. And so this basically is kind of sort of like an implementation. So if you have like multiple blocks. You have like the forward link. This is like a backward link. This is the next block. So the forward points here, and the backward point to another block in the same list.
Okay.
This also has like a forward and also backward link. Basically, writing these two pointer can removing this entry from the list is going to cause to write at the forward pointer this value.
Okay. Which is, I mean, this is basically, except for this part here, you're just describing a classic buffer overrun vulnerability.
Right. It was a buffer,
injecting code into a running process.
Right. So it was basically was some vulnerability in the application that was using the Heap Manager, but the exploit actually takes advantage of the heap algorithms to execute random code.
Okay.
It's not quite random, anyway, controlled by the hacker.
You got it.
So
random to the system anyway, but all code is random to the system.
Right.
Okay.
So now in server RTM and then in XP, SP2, several checks were done on this list. So basically, before we do the removal from the list, we validate whether the previous block. So this has to point like a previous block, and the forward pointer for this previous block has to point to this one, and the forward link has to point to the next block, and the backward pointer has to point to this one as well. So we validate whether we have this round trip backward, forward, and go back to the same block, and the same for the forward link.
Okay.
And this basically prevents writing some given value from the attack, unless you have this these pointers to point back the same value. This was actually quite efficient back then. But there was like a second level of vulnerability exploits where Matt Conover reported like about a year something ago.
Okay.
Another way to cause like an unaligned list to bypass this check. So it was kind of two steps attempt. And beside that was like another mitigation done in the header. Where back then I added like 8 bits canary, like a random value, pseudo random value based on the address, based on some other fields here, and with that we detect whether the header has been compromised. So an attacker has to basically put the right value here besides this. However, this is not very often checked, and 8 bits doesn't offer too much protection anyway. Okay. So it wasn't that effective. So this kind of creates like more of the settlement for Vista.
Okay.
Okay. So also for all the attempts. I said the first time was very reliable exploit. After that was closed, another attempt was to use the leukocytes. And the leukocytes are simply non-blocking single link list, and only the forward link, so a block in the leukocyte has the same header and has a link to the next block in the same leukocyte for the same size. This is not used, and this is whatever is the previous content. And in this case, a hacker can overrun the header and put a value here, which is going to be the next allocation that is going to be done by the Heap Manager. So let's say this was in bucket of let's say 32 bytes. And for some reason the exploit knows that the next allocation is going to have to be 32 bytes. It can overrun right here like a value, let's say foo, and the next time an allocation is going to be done, this foo is going to pop up in the head of the list, and the second time is going to be returned to the user. So basically, in multiple steps, an exploit can have an arbitrary write of this address. So once it's turned to the user, the exploit can use that allocation to write something there.
Absolutely.
So this was like the second with the involving local side. And in Vista, things change a little bit for various reasons. So one of the reasons is performance, and I mentioned has some implication in security as well. The Heap Manager by default had trouble scaling at a high number of processors, and configures high number of processors, it was a new front-end heap added a few years ago in server SP1, actually in server RTM, and then it was in a server SP1 as well, where this low fragmentation heap that was added later allows like scalability on multiprocessor system very well, up to a particular size such as 16K. However, an application needs to explicitly enable this low fragmentation heap, and require obviously recompile the application and some testing done with this new Heap Manager. The constraint with the heap management changes is, the trade-off here is like the application compatibility on one side, then if you have the security on one side, you have the performance on the other side. And heap management, like large-scale heap management changes, has to keep all three in a very good balance. We have to keep up the application compatibility. We have to enable better performance of large-scale applications, and on the other side, we also want to make less of a target for exploits, and make it difficult for, if some bug there's some application, to make much difficult to actually take advantage of that.
So now, if I could just interject, so it's kind of an interesting dance that you guys do, in the sense that you have to improve security, to increase security by actually doing more processing.
Right.
And at the same time, you have to increase performance, which of course can be adversely affected by the amount of processing you do. So you have to strike that nice balance.
Right.
And that must be pretty challenging from an engineering and algorithm perspective for you.
Right. That's one. And actually another interesting thing is, from a security perspective, let's say you have someone having a buffer overrun, and obviously from a security standpoint, you really want to block that application. You prefer to not allow running or crash or whatever, instead of having an exploit running code on your machine, stealing data, information, and so on. On the other side, there are some applications, like very old applications somewhere in the field, that they are not so visible from security standpoint from exploits, but you want them running to keep the high compatibility of the Windows. So what is and may not be even exploitable. Let's say that application never faces the net. It's like a very well contained environment. For those applications, like a very dramatic change for security perspective, it may decrease significantly the compatibility. So they have to support, they have to maintain, and they have to create a new version for the next version of Windows.
Yes.
I found actually the application compatibility bar kind of quite difficult, more and more difficult to meet than the one in the security and performance.
I can imagine.
And so now going back to this thing for
compatibility is hard.
Yeah.
Something we all take for granted. When we upgrade from OS to OS, yet our apps still work.
Right.
It's very important, because you don't want to throw away an asset that I've spent time making.
Exactly.
Just because I'm upgrading my OS. So yeah, compatibility. And that's incredibly challenging from an engineering perspective, as you just mentioned. So, good point.
And it's even more interesting on applications that are hosted or plugins or other code, like external code, where you try to make like a policy, like a very strong policy of the application, being like very secure. On the other side, you have something running the same address space or the same process, address space or the same process, very old plugin, no longer serviced, and it's very tough. How can you find the line to actually have all this scenario enabled?
Absolutely.
Or most of them.
Good point.
So now for Vista. As I said, the changes actually came a lot from the performance perspective. We wanted to have application performing faster and by default. So we detect a lot of performance or fragmentation problem at runtime, and automatically enable part of LFH, low fragmentation heap on particular sizes. I'm not going to discuss in detail all the algorithms about that. It's essentially we try to find the best performance we can get to the lowest memory footprint, and be open for highly scalable end server, or even like client machines, which currently may have like 2 processors these days anyway. Part of that was taking the local side out of the front-end heap and using the base anti-heap and the low fragmentation heap dynamically activated based on some criteria we found at runtime, and that to begin with kind of eliminated one of the surface area from the previous chain of exploits, like the Lucas side.
Okay.
Low fragmentation heap is at least to date it's much difficult to be exploited. So it has the header. So every block also has a header, and part of the header is like a pointer. Yeah, it's running out. So this part of the header, it's basically an encoded value to some list head for the allocations. So in order to let's say you have this block allocated, you want to release it, to free it. In order to retrieve the to make it successful free, you need to retrieve this region of the subsegment, this called subsegment, where the list head for this block is going to be. And this is an encoded value based on the address, is based on the heap and some other random value.
Now, can I just ask you, from somebody who doesn't think in these terms a lot?
Yeah.
The header is actually is being used by the Heap Manager algorithms to keep track of the memory.
Right.
When it's going to be released, where it's stored across the disk, or right. in the RAM memory, not disk.
Yeah.
So I just wanted to reiterate that it's a way for you to understand keep track of the pieces of memory you've thrown on the pile.
Right.
Okay.
Right.
Okay.
So that's the reason for that. And actually, we try actually to have like a double user to use this in also in the way that we can detect like something, some attempt of corruption or something happened there. So we kind of use this as a stamp for the header.
Okay.
And in LFH, even in server SP1, this was encoded, and there were attempts to actually go around this encoding and put a proper value here so that it's not causing a crash. But today I'm not aware of any way around this. So I just keep like as a very much difficult to exploit than anything else so far.
Okay.
And so now in Vista, a lot of the blocks, at least on the high, like large heaps, are likely to have this LFH enabled, at least for the blocks that are most commonly used, which means like automatically you have a higher level of integrity check on the heap when it's let's say released, and beside that, you have. Sorry, John said something.
No problem.
Okay, I'll ask you this one for a while.
Sure.
Now, besides this low fragmentation heap, in the regular anti-heap in Vista has the header of the block is also changed. It was modified and has some level of encoding. I think similar with the number of bits that are encoded in the low fragmentation heap. I think because it's there are some values which are kind of they're exclusive. So if you have like one value, you can deduct whether the other one is there. So you kind of have difficult to do the math to actually see exactly how many bits are used. since not all values are correct and not all combinations are correct, so you can basically have like aliases of the same good header checksum. But in essential, it has also some there's like some level of encrypting of the size of the internal structures, and the Heap Manager is going to to decode and access those fields every time this block is being touched, such as for free, or when you free a block, when you try to collect to the neighbors, the neighbor block. The all neighbor blocks also needs to be decoded to see if this is like a free block, or it's like what is the size, if you kind of the collecting the blocks makes sense or not. This becomes like actually a very common operation in the Heap Manager algorithm, and there is a pair for that, but I'm going to talk a little bit about this as well.
Okay.
But the advantage is like it's very tough to actually have a buffer overrun and go like closer to this block and not noticing the Heap Manager. There is a very good plus on top on this for for development and for debuggability. The corruptions and arbitrary writes are much earlier detected these days. So even on free build on retail bits. We used to have like page heap before. Actually, we don't have that one. Actually, I think that's the best debug functionality. However, even on free builds, we can detect a lot of the heap problems.
So for the people who don't understand out there, there's the check build, and then there's the free build. So you're talking about different builds that we use internally.
No. Actually, the check build it was not about the check build. We have like with the application verifier, which is like externally available. So the developer can enable a functionality called page heap, which essentially, the basic idea back then was to allocate the memory at the end of pages and have the next page protected or no access or like not committed, so that if someone tries to write beyond the buffer, is going to get an access violation instantly on that position. So it's very easy to detect heap corruptions.
Okay.
There's a light version of that where you don't allocate at the end of the pages because of the memory footprint. Sometimes it's not really applicable. So you have like a very large server having an allocation. Let's say it by taking like 2 pages of the address space is like it's very high footprint. And I saw cases where this was not really was not easy to use. So there is like a version of that called like light page heap where we have like some header checksums and things like that. You can detect on spot the corruption, but you can detect sometimes later like particular location overrun. And now embedding this part of in part of the header kind of provides a similar functionality with this on retail build and without almost no cost compared to like other retail feature. Okay. And having this detected earlier has this advantage that facilitates debugging and spotting the actual problem much earlier.
Excellent.
I was talking about this. Now, so for the performance, I said there's like some cost to this header encoding, and obviously the goal was to have the automatic tuning, detecting like part of the very common the common operation that happened in the Heap Manager, and diverting to the low fragmentation heap. So if someone, let's say, allocates like consistently some size and it has contention, let's say when try to allocate a particular size block size, then the Heap Manager is going to detect that one and going to enable the bucket LFH low fragmentation heap bucket for that size, and basically the performance is going to ramp up much better.
Okay.
And this actually has also some security implication as well. I think to the benefit of them, up to a point I can tell which one is. So the idea is like some of the exploits, like after XP SP2, were brute force attacks. So first attempt may get wrong because you couldn't put the canary in the first place, the cookie in the first place for the header. They might have to attempt multiple times, or like the next block was like a Lucas side block and so on. So they have to try multiple times until they get a successful execution. And the thing with this, if they try the same Vista, attempting to do the same operation multiple times actually changes the algorithms. So they actually may cause other problems. Now the drawback on this, I had a very good question for someone, is like, can someone actually find like a spot in some algorithms and trigger that one? And I think that's perfectly possible. The way that this is evaluated is today is that the low fragmentation heap header seems to be like much difficult to go through. So actually, moving toward a low fragmentation heap seems to be a better choice today.
Okay.
But this is like a cat and a mouse game. So
Sure. Somebody's going to find something.
Yeah, someone's going to find something, like another way to go around this, and like I expect to be much harder than before. It's going to be harder and harder, and actually already like I heard like from hacker communities that they try to see other ways. Some would even give up, like trying to do some heap exploits. They try to find other ways to
So that actually brings up a good question. In the course of when you're developing your algorithms, right, for the new Vista Heap management infrastructure, are you working occasionally with people to hack what you're doing? Like, look, I just implemented this new feature, try to bust it. Do you have that sort of interaction with people around the company, at least, like with security teams? You show them, here's my new algorithm, here's the changes I've made, let's see if you can break it. Do you have that kind of game?
Right. So I have some this kind of game with like inside the company, and also from outside the company. I also have some other contacts. They actually was I'll not hear like Matt Conover. So he was very actively, letting me know, like he found like some way around the heap exploitation, and I found very useful his feedback.
Excellent.
Now the Vista stuff, is like not. I mean, was out part of it in part of the beta. One is not entirely like as is today, and I don't think was really too much evaluation outside Microsoft. I think some people actually look from very high level on this. I don't think it was very
So in beta 2, you have a bunch of your work.
Yeah, so beta 2 has around a bunch of work, and obviously everything I said here it may change or may not change because as I said, we have this constrained application compatibility with security and performance, and we might have to scale back, move something around, and try to get the best balance on this.
Absolutely.
So it's not like like a product announcement or anything right now.
Absolutely.
It's just try to say like what is the work in progress for this.
Excellent. But let me ask you this: since you run in user mode, well, actually, it wouldn't even matter. I mean, in other words, you're not a kernel component.
No.
So theoretically, you can add updates to your DLL if need be on an existing platform, right?
Yeah. Right.
But of course, it's a compatibility and all that.
Right.
It's not something you want to do.
Right.
I understand.
Right. Well, the thing with this mitigation is like. It's a lot of abstraction done, like better abstraction done to the accessing the fields in the data for internal algorithms. So we have a lot of flexibility for Vista now to change it at run, not runtime. I mean in updates or from version to versions, a lot of the internals. So. I think this is a very good value as well to kind of keep up with like part of the the exploit attempts to go around the heap mitigations.
Now, just so from the terms of being a developer on this, what's some of the biggest challenges for you in the sense that you're going to have so many different processes wanting to use your algorithm simultaneously, right? You're the de facto heap allocator and deallocator.
But for
what's that from an engineering perspective? This must be challenging.
Well, if we set aside the compatibility problems,
Sure.
The main issue is really the performance. How can we make get the best performance for all these scenarios? Because have a widespread of application usage patterns, of allocation patterns, and memory usage. So it has to scale from like very small heap to large heaps, multiprocessor, multi-threads, and so on. So that's the challenging part. So the performance is basically the most significant in that perspective. Now, when you go to the application compatibility, this actually adds a lot more to this, to the problems we have to solve. So we have to think like this is like a common, usage, or how can we, allow this application to run, but also, enhance the security.
Mm-hmm. So now you work. Are you doing work with the memory manager? You communicate with the memory manager?
You mean the kernel mod?
Yes.
Yes, but it's very how can I say? It's like very limited.
Okay.
We just ask for like a large amount of memory.
And
just
manage
get it, and you just manage it inside, right?
Okay.
And for blocks of over 500, around 500K, all the allocation are directed to memory manager. We just keep track of these allocations so that I can free when the heap is destroyed, but we don't do
so
too much on that.
I'm going to ask a naive question because I want to. So what's the difference between like what you're doing and what a garbage collector would do? Right? I mean, you're allocating. The difference is that me as a programmer, I can tell you when to remove my stuff from the heap, and you'll do it, right? I'm just trying to ask because you use the term memory management on so many different levels. I want to make sure we differentiate between what you're saying, right? You're basically an abstraction layer to what's happening, sort of. So in other words, you ask the memory manager for a bunch of memory, and then you then allocate that, and then I, as an application writer up here in user mode, work with you. I'll say allocate this. And you do all the business of ensuring that you allocate it in a contiguous way, and then you provide what I need, and then I tell you I don't need it anymore, and you take care of it. Right? Is that pretty much what's happening?
Right. But you explicitly need to tell me when you don't need the memory.
But you are, so you're basically a memory manager.
Yeah, for example, right.
Okay.
Yeah.
Okay. Cool.
So.
Just took the relate. I just wanted to go off into outer orbit, but it's an interesting question because I think about, clearly I know what a garbage collector is and I know how it works, and so you allocate an object and you don't have to think about it anymore. It does the really hard work for you in terms of ensuring that it's going to be around when you need it. And then you still have to understand how memory works. But no, but the point I'm trying to make is you take care of memory. Very good. Okay.
So now, if
let's talk about it.
So if I to kind of put into perspective like how the memory manager kind of improves by default now in Vista. So well, this is kind of like some graph. So this is like let's say the operation per second. So the bigger the greater. So we have a number of threads here, and let's say if you look at the default Heap Manager that was, let's say, that was shipped by default in server SP1. Let's say this is like one thread, and you get, let's say, for allocation over like 1K, you get something like that. So as the number of threads increases, and you have a large number of processors. So I assume like you have like the number of processors increasing as well. The scalability was actually negative then. And even the looker size was negative because of the cache collisions. So the looker size were sharing the same cache line for multiple processors. So this was like kind of like very how can I say estimate graph, but it's kind of like that. If you go beyond the looker side domain, this actually goes something like that much early on. So here you have the contention cost. You have to pay here the coalescing cost, which is even present on single-threaded, and so it's like for, let's say, over 1K on 60 or 32-bit machine, and this is K, right? And this is like below 1K on a 64-bit machine. Now, if you look at the the Vista Heap Manager. So by default, because it detects a lot of the contentions and the problems such as fragmentation at runtime, the performance kind of goes something like that. So it goes linearly up with the number of processors. Let's say, just for the sake of making the point, let's say here's the number of processors you have. Let's say you have like 4 processors. You have 4 threads here. This is basically the point where you can scale more than linear because like there's no place to to run.
Yeah.
So it kind of stay steady. And the performance here is pretty much let's say 4 times in this case times performance like here. So it's like almost either scalability. There is, however, this gap here, which is like on single threaded. It could be, depending on architecture and depending on the scenario and some optimization, it may be between 5 to 10% slower on a single threaded applications compared to local site. Basically this is the cost if you want for the security, because the local site has, if you think about the issues with the local site, added more security as possible also to local site. But the performance was a little bit down because of that. So we tried to do some measurement to this as well.
Okay.
However, once you move to that point, it's going to be much better, regardless the size of the block, as long as it's below the limit of the low fragmentation heap. This scenario is quite common on high-end servers. And we saw that before, and when low fragmentation heap that they benefit from this highly scalable. And the advantage is that these days they don't have to do anything about that. We just run as fast as possible, as far as the heap concerned, on Vista.
So you're saying this is more performant, huh?
Yeah.
And you're not in marketing.
No.
I'm just playing.
No, it's not. I'm just trying to put like that.
It's fantastic.
Yeah.
Okay.
So now another thing that was a little bit interesting in FP, I mean Prevista, was there some patterns that could cause fragmentation, and the recommendation was to switch to low fragmentation heap, which switched to different memory algorithms. That was more appropriate for like large heaps and a particular distribution. So sometimes you can see there are some benchmarks which kind of exploit this pattern in the anti-heap, and because they take this at runtime, we have factors of improvement of like 100x sometimes on some patterns on the memory footprint and the costs of allocations. And very interesting in this scenario is applications that leak. So leaking memory sometimes can actually accentuate the fragmentation factors, because holds like a long-term allocation embedded with the short allocations. So the space cannot be reclaimed, cannot be coalesced, it cannot be reused for some other locations, right? And the Vista heap is much more resilient to those applications. It's not like encouraged to have leaks, but it's more like it's more resilient.
How is that?
Because once a site becomes very popular, it's actually it's allocated along with the other similar size blocks in the low fragmentation heap. And the fragmentation model is completely different than the first fit we have in regular anti-heap. And those blocks don't get coalesced, and they can be used for the same size as well.
Okay.
And other blocks that have like arbitrarily larger size in the anti-heap manager, that goes to the regular anti-heap, will have the opportunity to coalesce with adjacent block and so on.
Wow.
So as a model, it's more resilient to those leaks. But obviously, as I said, we don't want to encourage leaks, but it's more resilient to that. But there are some scenarios where we have applications have long-term allocations by design, and this fits in the same category. So
so for example, a service that's always running.
Right, server that's always running and keep part of the locations,
For sure.
For some reason, for a long time.
So can you, at your level, can you detect when a can you detect when a memory leak is happening? I mean, how could you do that?
No, we can't really detect that. No, we don't detect this at runtime. It's just the way algorithms can tune themselves to enable some. A better memory efficiency in some scenarios. We obviously cannot detect leaks, but at runtime, it's actually we have some tools to enable detecting, actually helping application developers detect leaks. Yeah, there is like some question mark around this because so the algorithm is looking for busy blocks not referenced in the process, and may not necessarily be leaks because could be some people encode pointers to blocks, so we can find a reference. They might be in kernel mode first.
What if it's from a different thread?
That's fine. No, it's just if it's not visible in the user mode for some reasons.
Okay.
So yeah, it comes and goes with several false positive and false negative situations. So it's not like a deterministic way to say, yeah, you have this block, it must be leaked. Yeah. So developer needs to actually analyze the block allocation and can tell whether this is leak or not. And actually it was very successful, even it was like some rate of false positive and false negative, was very successful to catch a lot of leaked blocks, and very, very helpful in development. But this is a very extensive operation, takes a very long time. But it's possible to run on Vista also on dump files. So if you notice, for instance, your server, your application, it's taking a lot of space, you can just save a dump file before you restart the machine or restart the service, and you can do the analysis offline on that dump file.
You have to know what you're doing to read it. Give it to a developer.
Yeah.
To a system guy or girl. You know it. Right. So what I'm hearing from you is that Vista takes more advantage of the low fragmentation heap.
Right.
And therefore guarantees arguably maybe more stability.
Right.
Application stability. In that sense, since you have contiguous, as you were saying earlier, you think that it has anything to do with it?
No, I think it's tough to put the application stability, because if you think actually detecting some of the problems early on may actually crash an application earlier if you make the choice to be more secure than current application compatibility. And in fact, it's this was like one issue that was we considered a long time ago. It's like even in server SP1 and XP SP2, when you detect like a heap corruption or some inconsistent heap state, the default was, the last notice out there was that we don't do anything. We try to kind of prevent like do an arbitrary write, because that was like the one that they tried to get, like the hackers tried to get to.
Sure.
But we try to keep the application alive for the compatibility reasons. Now, in Vista, we have a way for an application to opt in for a model where the application gets terminated right away at the first inconsistency check. And this is very useful, basically, to kind of get out of the way of the exploits. At first time, we detect something, and now, so let's say I run IE, and I see like something I don't know, go to some web page, something is crashing. I don't know, could be like an ActiveX, could be, I don't know what could be there. But essentially, I'm more confident that if I get a corruption, I'm more confident to just crash the IE right away, as opposed to just wait for for that code, malicious code, to run on my computer and steal password, install rootkit and whatever.
Yeah.
Right.
So, but let's talk about that real briefly. How do you detect a heap corruption? What does that mean?
So
What's a heap corruption?
So heap corruption is like it's corrupting of the heap states, such as the header. That's the most common.
Okay.
And actually, we use the advantage of having the metadata embedded with the allocation data, with the user data, to have this some sort of how can I say, like a seal of the block, right? And every once in a while, for the heap operation, you have to touch some of those, heap internal structures. And at first one, we detect that something is inconsistent. If that, option is enabled, we terminate the process right away.
Understood.
Right.
So it's a corruption of the header file.
But the application is to opt in for this. Yeah, to opt
why?
in for this behavior.
Why is that? Why was that policy made?
Because of the application compatibility.
Well, but let's talk about that for a second. For example, if you have a policy on the system where any application that's running, if there's heap corruption in its process, that's tied to its process, that you know of, because you're the one who's managing the heap for that process, kill it. So where does the compatibility issue come in? By opting in. That means that I would have to recompile my Netscape 4 application, for example, to opt in to being closed when it gets hacked with a heap corruption vulnerability.
Right, which means you need to test it with a new heap. You need to do a lot of extensive testing with that scenario, because you have to build it and make it more up to the application developer to make this decision. I think.
But what if But the problem with that, I would argue, is that what if the application developer makes the wrong decision? Like, is it ever a right decision to not crash if there's heap corruption in your process?
Yeah, let's say, I don't know, I have I'm trying to find an application I have found. No, I don't know. Let's
application
say
X.
Yeah, let's say I have some video editing which doesn't communicate with anything on the on the network. It doesn't even load anything like that. I just want that to run. I don't care if it has like corruption and. I don't want to get that destroyed. And I think a lot of applications don't really, are not like network facing.
Understood.
And I think it would be probably a good policy to make it like the network facing. But even in that case, maybe there are situations where they have like, there are some other mitigations in place, particular that application.
Fair enough.
So.
But like everything we do in Windows, we're trying to make it as general purpose as possible and give people as much flexibility.
Right.
And I'm not. I'm not in marketing, so I could be accused of it. I mean, that makes sense. I mean, you create a really general purpose operating system. You want to make it easy for developers to build what they need to build. In the end, for consumers to get to use what they want to use, and then feed that back to the developer to build what the consumer wants to use. Blah 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 blah. So you have a hard challenge of making a very general purpose, highly tuned killer machine.
Yep.
So. Great. It's great to hear that you've done a lot of great work in Vista. And I hope to see some performance improvements. Not that XP was that bad. I mean, I have.
No.
I think the kernel rocks in XP. But.
Yeah, no, actually, as I said, I think a lot of the performance that was done in Vista can be seen on a machine with multiple processors.
Okay.
As from the heap perspective.
Okay.
I think the local size for one single processor machines was as good. Actually, I told you before, it was actually even better, like within some margin for single processor machines. There are other things addressed actually for large, even if it's single processor addressed in Vista, where you can scale better for large heaps, and it's much performance based, have better locality on 64-bit platform by default as well. But I don't think from like one processor, one of the the low-end machines is going to be much seen right away. It's more the security side that probably is more important from that side.
Sure. Now let me ask you real quickly, since our audience are mainly developers and architects and stuff. Your algorithms are mainly proxied from Win32, right? So in other words, do I call your stuff directly from my app?
Yeah,
I
but
call Heap Alloc and Heap.
yeah, Heap Alloc just. I mean, the Win32 has very thin layer, so
It's a very thin layer over you.
Yeah,
And
yeah.
I, as a Windows programmer, I'm usually programming
Yeah.
to you via Win32.
yeah.
Have you added any new APIs in Win32 towards you, or have you done any work in the API department for?
For the heap management, well, there are some new class informations for the, like this one to break on failures.
Okay.
But I mean, nothing significant.
Okay.
Nothing
Just
significant.
core engineering has gone
Yeah.
excellent, gone up. I mean, more good.
Yeah.
Don't want to end on that note. Core engineering is gone. Yeah, right on. Anyway, great to have you on again.
Yeah, thank you.
And we'll talk
Thank
to
you
you
for
again for the next version of Windows, huh?
Okay.
Or maybe we'll
Thank
see
you.
what's new. So actually, since this is beta 2, you're going to want feedback, right?
Yeah, yeah.
I mean, you'd love some feedback from system developers on the work
Right,
you've done. If they've
right.
found any problems at all, or
Right.
even good feedback.
Yeah.
All
I think
right.
we got so far very good feedback from beta 1.
Okay.
And this was like where the bulk of the changes were.
Okay.
So I think now even better broader coverage is is going to be much more helpful for me to get like a better idea about how the compile and how the performance and all this go together.
Fantastic. Well, thank you, Adrian.
Thank you very much.
See ya.
Yeah.